Yeah, I think, let me check. Yeah, we have. Let's wait for a while.
Okay.
I think Hoyle just sent you a message.
Okay. Oh, right, I can see a little something here. Let's click on that and see what happens. Nothing.
Oh.
Oh, here we go, chat.
Yeah.
From Magnus Johnson to all panelists, indeed. Oh, okay, sorry, there's a cool background. I'll explain, John, I'll explain. Yeah, very nice, very nice. Okay, so this is going to be an entertaining session then. Good.
Yeah, I think so. Perhaps I should start share my screen and then you can, yeah.
Yeah.
Yeah. So, okay, wait for a while. Yeah, so it's time to begin. Hello, everyone. Welcome to today's Platform webinar. So I'm Tenten Chen from Professor Wei Xiong's group, and I will be the host of today's talk. Before we start, I would like to make a few announcements about future schedule and the mechanism of our talk. So the first, the Journal of Chemical Physics will have this special issue of Platon chemistry, molecules in cavity and plasmonic media. And the editor will be Professor Jason, Professor Shagai, Wei, and Hoel. And you are all welcome to contribute. The submission deadline will be October 16th this year. And our webinar will be held every Wednesday at 9 a.m. Pacific Standard Time. And the registration for each webinar can be made through this link here. So, here is also the schedule of our future talks. And also what I need to mention is that we will also extend our webinar invitations to postdocs as our panelists. And the first group of postdocs invited are Dr. Christine Anadottir from University of St. Andrews and Dr. Bing Gu from UC Irvine. And in fact, the first postdoc spotlight will be held next week. And also recently we have created this Platon Chemistry online community webpage on Facebook, which allows everyone to share papers and post announcements. You can search by its name. Meanwhile, we have also uploaded our recorded videos on this Platon Chemistry webinar YouTube channel. And for those who missed the talk, you can subscribe it and watch the videos later. Finally, I would like to introduce the mechanisms of this webinar. During the talk, all attendees are muted. For those who have questions, you can click this raise hand button here, and I will interrupt Professor Bill Barnes at the appropriate time and enable your audio to ask questions. Also, sometimes you can type in your comments or ideas using this chat function here, which I think somebody already did, so that you can share with everyone. And for Q&A here, you can type your questions there, which will be addressed at the end of the talk. So for the questions that are not answered due to the time limit, we will collect and send to the speaker after the talk. Now let's move back to today's webinar. So it is our great honor to have Professor Bill Barnes from University of Exeter as our speaker today. Professor Barnes received the Bachelor of Science and a PhD in physics from Exeter in 1983 and 1986, respectively. From 1986 to 1992, he was a research fellow in the Optoelectronics Research Center at Southampton University. In 1992, he was appointed to a staff position at Exeter. He is currently a physicist at the University of Exeter, and he also holds the appointment of chair of complex plasmonics in the complex optical and photonic systems group at the University of Twente in the Netherlands. He has received many well-recognized awards, including the Royal Society Wolfson Merit Award in 2004, elected Fellow of the Optical Society of America in 2008, and elected Fellow of the Institute of Physics and the Thomas Young Medal and Prize in 2019. His main research focuses on looking at how molecules interact with light. This is a topic he studied in his PhD, put on hold during his postdoc time, where he worked on fiber amplifiers and lasers. When he took up a staff position, he returned to look at molecules and light. Since then, his main research has been in plasmonics, molecular energy transfer, and now strong coupling. Today, he will give us a talk entitled as Linking Molecules with Light. Now let's welcome Professor Barnes. Professor Barnes, now you can share your screen.
Okay. Let's see if we can make it work.
Yeah, it works.
That's good?
Yeah.
Okay. All set? Okay.
Yeah, all set.
Thank you very much, Cheng Cheng. Well, hello everybody. Isn't this incredible? This amazing seminar series that I'm really delighted to be taking part in, and it's just such a fantastic thing. It's a series that none of us could have organized in our home institution. Really wonderful thing, and a great way of helping to keep the momentum of our community going. I'd really like to thank the organizers a lot for that. I think they've done a fantastic job. And I'd like to thank everybody who's taking part today and for all the other seminars as well, because it's really helping to keep our community going. Wonderful. I don't know whether you can see a picture of me in the top of your screen. I don't know. I can't, it's disappeared from my screen. But if you can, you might notice that I'm in a rather strange place. I'm actually in the cellar of our house at home. And I'm in the cellar for two reasons. One is that this is the best Wi-Fi connected room in the house, so it's a good place for me to do this talk from. And the second is that I'm actually trying to get some spectroscopy stuff set up in the cellar, because I've got an undergraduate project at the moment to look at the pigments in illuminations of medieval manuscripts. Clearly, we can't look at medieval manuscripts at the moment. That's unfortunate, but the students have been doing a fantastic job. They've been supplying me with paintings of illuminations, and I'm trying to take some reflectivity spectral data, so that they've got some experimental data to work with for their project, and that's been a great thing to do over the past few weeks, really good fun. Before getting underway with the kind of main content of the talk today, I'd like to just introduce the key people in the current team who are working in the topic area that I want to talk about. Two PhD students, YJ and Milo, and Milo's work on metamaterials will form kind of a big fraction of the latter part of the talk today. And then postdocs Philip, Kishan and Adarsh, and it's Philip's work that I want to talk about early on. in the talk this afternoon. There are two past group members I wanted to mention, Henry, who's now a postdoc in Aalto, and Sathya, who's now working for a UK startup company called Metaboards. I also wanted to thank the technicians who work with us in the physics department in Exeter for a fantastic job in actually helping us undertake all of the experimental work that we do, and for taking an important part in helping set things up for the work that I want to talk about this afternoon. Well, let me just give you an outline of the talk that I'd like to give you. There are three parts. In the first, I'm going to talk about using ellipsometry to probe strong coupling. And then in the middle, I wanted to give a bit of a break, really, to provide a bit of an interlude, if you like. And I want to spend a few minutes there just talking about this really important interaction when we're looking at how molecules and light are coupled together, this D.E interaction. D is the dipole moment of our molecule, maybe, and E is the electric field strength. And then in the third part of the talk today, I want to talk about metamaterials and strong coupling. And I'm really very happy to be able to talk about both these topics, ellipsometry, metamaterials, with you today, particularly because this is unpublished work. It's not out yet, but nonetheless, I think it's got to a stage where it's really interesting stuff to talk about, and certainly something that's exciting us at the moment. Okay, so topic number one then, ellipsometry. Ellipsometry is a technique that's very well established, used in many material science labs and so on, but might not be familiar to all of you. So I thought it might be worth just introducing that to you. Here's a picture of the ellipsometer in our lab on the right-hand side here. And the idea really is that we're just looking at the way light's reflected by some sample sat on the stage in this setup. Incident light comes in, some angle of incidence theta, and it's reflected, and we look at the reflected light. This might look very familiar. We do a lot of optics this way, just looking at the reflected light, but usually we're interested in measuring the intensity of the reflected light. In ellipsometry, we take a slightly different approach, and here we try and retain the phase information, the phase change that takes place on reflection. So we want to make use of that phase information. And really what I wanted to show you is that if we retain that phase information, there are other things that we can probe in the strong coupling regime. The idea is that we look at the output polarization for various different input polarization states. That's how we can build up this picture about what's happening in the phase. Now, there are three parameters that people in ellipsometry work with. And they're given with this equation here. So the usual parameters one hears people talk about psi and delta, the strength and the phase of the signal. But the key point to look at here that might give you a point of contact if you're not familiar with ellipsometry is that the parameter we're interested in is RP, the Fresnel amplitude reflection coefficient for p-polarized light, divided by RS, the Fresnel amplitude coefficient for reflection for S-polarized light. And that gives us basically a complex number rho. And what I'm going to show you is results from looking at ellipsometric measurements for strongly coupled systems. And we're going to be working with these three parameters, rho, psi, and delta. Now, to give us some kind of reference point, some kind of starting place, I've chosen to look at what happens when we just have a thin silver film on a glass substrate. So the little schematic top right here shows us that we've got light coming in, incident on a silver film, and then reflected, and we're going to do these ellipsometric measurements. So in the panel at the bottom left here, you can see that I've got these two parameters. The black line on this panel is tan psi, that's one of the ellipsometry parameters, and I've plotted that here as a function of energy of the light. So we're going from the red part of the spectrum at 1.5 electron volts out into the UV at 3.5 electron volts. And you can see that tan psi doesn't really do very much. Similarly, we can look at this other parameter delta. Delta also varies as we go across that spectral range, but again, there's not very much happening. And this kind of rather boring looking picture is simply because silver doesn't change the way it responds to light very much in this spectral range. It just reflects light really rather well. If we now change slightly and look at the parameter rho, then on the right-hand side here in this panel, the right-hand lower panel, I've plotted here the parameter rho in the complex plane. So we've got the real part on the x-axis and the imaginary part on the y-axis. And you can see over the spectral range that we're interested in, we get a fairly simple looking thing. There's just a bit of a bent line, and that's it. That's what silver does in this ellipsometric measurement. Now what I want to do is to make things a little bit more interesting and take them closer to the kind of system we might be looking at, and to make a little Fabry-Perot metal-clad microcavity. So let's look at that next. However, before we do, I just want to point out that this parameter rho, which we're looking at in the complex plane, we can also look at in a 3D variation, where we've got the complex plane down at the bottom, and then we just show the trajectory in the complex plane as a function of energy. And that's really rather nice, and we'll make use of that later on. Okay, so let's go and look at a microcavity. Here we are. So again, the schematic on the right-hand side shows a polymer microcavity. The polymer here is PMMA. There's a silver film on either side that's making up the little microcavity. And on the left-hand side here, in the left-hand panel, we've just plotted the intensity for P and S polarized light as a function of energy for the particular angle of incidence that we've chosen. And you can see a nice clear reflectance dip there where we couple into the cavity mode. And for the two polarizations, we get a dip at a slightly different spectral frequency as we'd expect. The cavity modes are sensitive to polarization when we're away from normal incidence. So that's nice, and that's the kind of measurement that we're generally very familiar with. Now let's add to that what we can find if instead of looking at the intensity, we do this amplitude and phase measurement that the ellipsometer allows us and record those parameters instead. And now things look really rather more interesting than they did for just the silver film. Again, in the lower left panel, you can see we've got psi. There's some really kind of, that's the black line there, some big feature happening around 2.3 electron volts. Similarly, the parameter delta is showing something very interesting going on. But I think maybe the most useful way to see what's happening is to look at this parameter rho in the complex plane. And you can see that the simple line that we had for just a bare silver film now has this huge great loop added to it. And it's this loop that's really of interest to us. And if again we look at that in a 3D plot, you can see even more clearly what's going on, I think. So here's the complex plane again, and the trajectory of this parameter rho as a function of energy. And this loop here is really associated with the cavity resonance for this little microcavity. So that's very nice. We get a really big, strong loop when we hit a cavity resonance. We could make our cavity thicker, and if we were to do that, what would we expect? Well, we'd expect to get a whole series of resonances now, because the thick cavity can support lots of different order modes. And again, if we look at the ellipsometric parameters, there's lots of stuff going on. Look at this plot of rho in the complex plane as a function of energy, this 3D plot. And you can see this nice staircase now of 3 or 4 nice loops. And there's a loop for every cavity mode. So many modes, and we get many loops. Okay, so we've got an idea now about how ellipsometry can be used to probe a cavity. Let's take the next step then and include something interesting inside the cavity. And what we chose to look at for this was a system that's a direct copy of a lovely piece of work from the Everson group, who've done so many wonderful things here. In this case, a paper that came from 2011. And it's a lovely piece of work here, particularly because it shows something really rather nice that we managed to make use of in this ellipsometric study. The cavity here is one where the polymer is, again, PMMA, but it's doped with a very interesting photochromic molecule. in its inert state, spiropyrin, or SPI, as we've got it here, is transparent. So we're going to expect this to look much like the system we've been looking at in the last couple of slides. But here's the interesting thing. Take spiropyrin, illuminate it with ultraviolet light, and the molecules undergo a photochromic transition. And the spiropyrin gets converted to merocyanin. And merocyanin is a very strongly absorbing dye molecule with a lovely strong resonance at 2.2 electron volts. So this is a great system for us to work with, and one of the things that we wanted to do here was to look at this change from having an inert blank cavity to one full of molecules with a very strong resonance. And here we've got that fantastic opportunity of doing this by just illuminating it with ultraviolet light. Okay, so let's look then at the kind of thing that we'd expect in a typical strong coupling experiment. Not ellipsometric at this point, but just the standard way of doing things. And so what we're going to look at is both what happens in reflection and in transmission. So here we are. Look for the moment, if you would, at the left-hand panel. We've got here reflection for p-polarized light, the intensity of reflection plotted as a function of energy. And the blue curve shows us what we get from this system when the molecules are in the spiropyrin form. And it's an inert cavity. We just get a nice single dip there indicating that we've hit a cavity resonance. Now if we illuminate the sample with ultraviolet and we convert the SPI into this colored form, merocyanin, you can see there's this really large scale splitting. We've got a splitting here of something of order 500 MeV, huge splitting. If instead we look at transmission rather than reflection, and in particular, if we look at transmission as a function of angle, then we can do this nice thing where we can take the data from that kind of an experiment and assemble them in the form of a dispersion curve. And that's what we've got on the right-hand side here. So the right-hand half of this right-hand plot shows experimental data from this system when it's in the merocyanin form. And on this plot, what we can see is the position of the molecular resonance is the horizontal red line at about 2.2 electron volts. There's a green line showing the inert cavity mode, and then you can see the very large splitting and the dispersion of the two modes, these two new hybrid states, the upper polariton and the lower polariton. And then on the left, just to make a comparison, we've got data from a standard multi-layer calculation to make a comparison with the experimental data. So it's very nice. We get a lovely transition from the spiropyrin form to this colored merocyanin form, and we get this wonderful large splitting. So it's a really great system to have to be able to look at what's going on and particularly to probe this transition. What I'd like to do next then is to just look at that transition. So what we're going to do is start an experiment in which we have a sample in the spiropyrin form, and then gradually let the experiment evolve as the sample is irradiated by UV light. And the great thing that we discovered in doing this was that we didn't have to do anything extra. The ellipsometer light source actually produces ultraviolet light, which we weren't aware of at the time. So gradually over the course of an experiment, whether we wanted it or not, our molecules were being converted to the merocyanin form. And here are the kind of data that one can see. So on the left-hand side, we're looking at reflectance. So I've got the same traces that I had on the previous slide. The blue curve here in the top panel shows the reflectance for the spiropyrin form. And then as we illuminate the sample, we get the red trace. And you can see the correlation there with the plot underneath. What does the plot underneath show? Well, it's also showing reflection, now on a color scale. So yellow regions are high reflectivity, blue regions are low, and it's as a function of energy again. But then what's happening on the other axis is we're just letting time evolve, and you can see there that it's a logarithmic scale. So as time evolves, the deep reflection minimum at around 2.2 electron volts gradually changes and then very quickly starts to diverge. And we've got these nice new two hybrid modes, the upper and lower polariton branches. Well, what we can show now is that if we look at that same system, but rather than plotting the reflectance, we look at the ellipsometry parameters. The top two panels show delta and psi again, but look at the bottom panel, I think is maybe most informative here. We're showing here cosine of the parameter delta, again as a function of energy on the x-axis and time on the y-axis. And one can see there's a very strong signature, again around 2.2 electron volts for the unilluminated sample. But then as the illumination kicks in and the spiroparin is converted to merocyanin, we can see again this split takes place, and the ellipsometry parameters here are tracking very nicely what the reflectance measurements show us in the left-hand side.
Hi, Bill.
Hello.
Yeah, we have. Sorry to interrupt. We have a.
Not at all. That's good.
Question.
I'm glad people interrupt.
Yeah. So yeah, we have.
Hi.
Hello.
So my question is about the what is the angle of incidence for the light when you measure these ellipsometric parameters? Because if it's 0, then shouldn't it be exactly the same? Like P and S polarized light should look exactly. The results from that.
Yeah, you make a very good point. If we were looking at normal incidence, you're exactly right. P and S should show the same thing. Most ellipsometers work in a slightly different way, and in fact, the technique really requires us to work at an angle that's not normal incidence. So, in the data that I'm showing you here, we're working at an angle 60 degrees away from normal incidence, and so then the two coefficients P and S are not the same, and that actually is the key to giving us the information.
Okay, thank you.
Is that okay?
Yeah.
It's a good question. Thank you for that. Okay, so there we are. We've got a comparison in this slide then between what we see in the standard kind of reflectance measurement and on the right what the ellipsometric parameters are showing us. But maybe at first sight it's not so easy to see whether there's something really significantly different about these things, or whether one's a better way of showing what's going on or not. Rather than looking at the parameter delta, which is what we have on this slide, let's instead move to look at what happens to these three different parameters. So on the left-hand side, top left, I've got the parameter psi. On the bottom left, we've got the parameter delta, but the one I'd like you to focus on is the panel on the right-hand side, the big one. I've just reproduced here the panel for the spiroparin. This is the empty cavity, okay? And so this basically is the silver response here. And then what happens is at some frequency, some energy, we match to the cavity mode, and we've got this nice big loop. And to be clear, then we're working with spiroparin. We're at a very early stage in the illumination, so really very little of the spiroparin is in the merocyanin form. It's basically just a transparent dielectric filled cavity. Now let's see what the loop looks like as we increase the time and therefore increase the amount of merocyanin in the cavity. So here we are for 220 seconds into the experiment, and you can see two things. I'd like you to try and spot the two things. So the first is that the size of the loop has been reduced. And that's because we've now got quite a lot of absorption in our system, so the resonance has been damped. The second thing, which you might have spotted already, is that there's this kink in the corner of the loop here. A kink has produced a corner, if you like, in this loop. And I'd like you to keep an eye on that thing, because if we go down to a higher level of exposure and convert more molecules to the merocyanin form, then we get this green trace here. The loop's smaller, more absorption, but look at this. There's this lovely little extra loops just cropped up. And if we expose even further, that loop becomes bigger still. So just let's go through those sequence there. We go from having no kink to a little loop and then a bigger loop. So the thing that we're interested in at the moment, and we're trying to sort of just get ourselves sorted out about, is to try and understand whether we can use the appearance of this loop as a way of monitoring whether we've made a transition into the strong coupling regime. Rather than get stuck in a detailed discussion about different kinds of strong coupling criteria, I actually wanted to do something slightly different. I wanted to ask a rather broader question, which is, okay, this looks very nice, but is it a generic property, or is it rather specific to the sample that we've chosen? So what I'd like to do now is to just show you two other experiments we've looked at. The first is to take the experiment.
Hi, Bill.
Yeah. Yes, hello.
Yeah, so we got another question. Sorry to interrupt.
Good. No, that's good. I said before, questions are good.
Yeah, hello.
Hello.
Yeah, so I was trying to understand, like, in the tan psi plot, like initially it was like that big function, that function, right, the blue one. But now
Yep.
it as time progresses, it kind of develops into two wells.
Yes.
So can you can you tell something on that? Why does it behave?
Well, I suspect I can't tell you much more than you've already described for me. I think you've described it very well. What we see is that there's essentially one spectral feature there, a kind of a first a dip and then a maximum, which is a classic kind of signature that you might expect of many kinds of resonance. We see one kind of feature, and then what happens as time goes by and we introduce these molecules into this cavity is that feature somehow spreads out spectrally and becomes two rather distinct entities. So again, I think really what we're seeing here is that the parameter psi, and in fact it's in the lower plot as well in delta, they show the same thing that you see in various other ways, whether it's by reflection, transmission, or whatever, that we see a change in character of the system. As we crank up the number of molecules in the cavity, we go from a single cavity resonance to this situation where we've got two distinct resonances. So I'm not sure I've asked your question very well, but I think you've already made the important observation. One can see this change in behavior from a single resonance to a double resonance. Describing the exact nature of the change seen by the parameters that we've got here, then I think the most useful way to do that perhaps is to go through some modeling and just try and see how the shape of the different functions here varies with the kind of parameters we might expect to vary.
So that two well is like the two wells that develop due to coupling. Like
yes, I think that's right. I think if I've understood you right, I think you can envisage those two wells, whether it's exactly the minimum or not, it's another matter, but you can associate those two features with the formation of the polaritons, yes.
Okay.
Does that help?
Yeah, thank you.
Oh, it's a great question. Thank you for that. Okay, so
Hi.
hello.
Hi, Professor. We have more questions. Sorry to interrupt.
Good. Let's keep going. Yeah.
Sorry, Bill. I just have a very simple question. So, at time equals 10 seconds, right before the photochromic transition, can you again what is the origin of this anti-crossing type feature in these plots in the right-hand side? So right, like in the blue.
Yeah. Okay, so I think we have to be quite careful about whether we're looking at an anti-crossing or not, and that's why
I don't think it's anti-crossing, but can you explain to me why do you have like that gap where, like, for a fixed real part of the road you have two values of imaginary?
I suspect I can't give you the answer that you want, so I'll make it very brief, and then you can either answer me another question or I'll have a good think about it, and maybe we can talk about it another time. What we've done is we've taken the response of a silver film, which was just this kind of simple curve, and we're adding somehow this big loop, which is the cavity resonance. And if I was to plot this thing in 3D, then you could see very clearly how the trajectory has this extra loop added to it. Exactly whether we see a crossing point or not here is going to depend on how our trajectory in this 3D space looks.
So then these two imaginary values of rho correspond to two different energies then?
Yes, they do. Okay, yes, exactly.
Okay. I see.
That's
Thank
right.
you very much.
Exactly. No, that's a pleasure.
And also, yeah, sorry.
Yeah, good. Okay, this was a good slide. Good. Yeah, far away.
Yeah, so.
Hi, Professor. Sorry to interrupt you.
No, please don't apologize. It's what I'm here for.
Yeah, what I can learn from your experiments that these experiments that you are doing it in the visible regime. So
yes,
should I expect a reversal of this loop if I do it under UV regime? accompanied by the back isomerization of the molecule from myrcene to spiropyran?
That would be a very interesting thing to do. Yeah, I don't know what to expect because I'm not familiar with what the UV response of these two different molecules looks like. Maybe you have an idea about that, but I think the idea of being able to track what's happening in the UV here with a similar technique would be a really interesting one. I know we are trying to track what happens out in the infrared at the moment. So yeah, if you can probe this system in a different spectral region, and I think the UV, it should be interesting, shouldn't it? Because, you know, that's where the transition is being made from these one molecular state to the other. So yeah, nice.
Thank you.
And we have one more question. Hi, I think Gilad, you can ask questions.
Hello, Bill. This is Gilad Aran.
Ah, Gilad, hello.
Hi. So I'm trying to relate the position of this extra loop that you get, the spectra on the left. So where does it appear energy-wise?
Okay, you're going to have to be generous with me and let me move to my next slide because I think I have the information you want on it, and maybe it helps you, maybe not. And if there's still a question, so let me just do it now. So, so in the top row here, we're looking at the same kind of idea, but we've swapped dyes. We've moved from the Merisine into the standard that everybody, including ourselves, uses, which is this lovely J-aggregate stuff called TDBC. So here, on the right-hand side now, I've got this double loop thing, and I've been trying to indicate, or we've tried to put on there a red arrow, and then on the left-hand side, we've put a red arrow in basically to indicate the middle of the response of what's going on. Really, to answer your question properly, and actually to answer Joel's, we'd need to give you the plot that's got the 3D trajectory for rho in the complex plane as a function of energy. But I don't know whether this gives you a starting point, but.
Yeah, I think that makes sense. Yeah, thank you.
Okay, okay, good. I mean, so thank you for the question. They're all good. There's wonderful to get these. So this top row here is basically, we did this experiment to check that this extra loop behavior is not just a quirk of the one particular sample we looked at. We've now got it from two different dye samples with two completely different dyes. We wanted to go one step further and just see, well, okay, is this actually a generic effect for strong coupling in general, not even necessarily involving dye molecules? And the answer is yes. Because here on the bottom row, we've looked at coupling between a waveguide mode. In this case, it's a hafnium dioxide waveguide layer, and the plasmonic surface lattice resonance associated with a corrugated gold film, as indicated in that sketch over on the left-hand side here. And again, if we go over and look at the loop structure, you can see we've got this loop within a loop characteristic again. We've got a loop for our waveguide mode excitation grating coupled, and we've got this extra loop because we've actually generated a hybrid mode that's part plasmonic lattice resonance and part waveguide mode. So it does look, at least at the moment, as though it's a generic kind of behavior for a strongly coupled system. Clearly it's early days, and we need to look at this in more detail, but I think it's a really interesting starting point. Let me try and summarize for you what the ellipsometry approach offers here. It's a commercially available system. It's quick to use, it's low noise, and the important thing is that we get amplitude and phase spectral information. And we're trying really to make use of that phase information to see if we can just look at our samples in a slightly different way. There was a great question a little while ago about could we do something in the UV? Our system won't go down that far, but one can get commercial systems down to 130 nanometers. And one can also get commercial systems out to 30 microns. So there's a prospect here of covering a huge spectral range, really the range that matters for molecular systems from the UV out into the infrared. It looks like we have a new candidate signature for strong coupling when we look at the ellipsometric phase data. And although we don't have a published article yet, we do have something on the archive. So if you want to go and take a look and find out more there, then please do that. So I'm looking at my little watch here and thinking, middle section of this talk, probably not a great plan. So I'm actually going to skip straight through that because I'd like to keep the theme of focusing on experimental work. So excuse me while I slip through a few slides here.
Hi, Bill.
Yeah.
Yeah, we got another question.
Good. Let's have it. Next question, please. That'd be good.
Hello.
Hello.
Yeah, so I know you didn't really want to get into the discussion of all the different definitions of strong coupling, but
You're quite
as
right.
far as that third bullet point on the the summary slide, I was curious. So can you interpret the number of loops as the number of resonances and the
I think that much we can. I think. Okay. Sorry, go ahead.
Yeah, no, yeah. So I guess if the answer is yes, then can you interpret? So how does it seems like the transition between two loops and one loop represents some sort of, like the point when strong coupling arises. So like, do you know if that aligns with other definitions of strong coupling?
Yeah. So let me give you the kind of short version. You can find some more details in the archive paper, and hopefully when it's published, there'll be a slightly fuller analysis as well. But the key thing is that you've already picked up is that basically you can look at the transition from one loop to two and say, aha, did we get strong coupling? And the answer is, simplistic answer is yes, but one has to be careful, okay? Because here we're probing our sample with a very specific angle of incidence to look at it. And if we were to probe it at a slightly different angle of incidence, we'll find that the loop cuts in at a slightly different concentration of molecules in the cavity. So care is needed, all right? Just as care is needed in trying to interpret your data if you're looking at reflection or transmission or absorption or extinction. It's not a simple business. And in the archive article anyway, we make a comparison between a number of different criteria. So it's a interesting topic to look at, but one very quickly gets bogged down in some quite important but nonetheless very detailed aspects about just exactly how we are going to make that decision about which regime we are in. And I guess I might add a little extra to that and say that really, if we're interested in trying to do chemistry or materials science with strong coupling, we shouldn't be worried too much about whether we're just inside the strong coupling regime. We need to be well inside it. So, there's some thinking to be done there as well. Does that help?
Thank you so much. Yeah.
Yeah, lovely. All right. So it was the right choice to skip the middle part then, so we can get underway. So I want to tell you about something else. So actually on this slide, this is the kind of motivation for what I want to talk about in the rest of this session. So I've taken the schematic from the literature. It'll be familiar to many of you. It's a schematic that's really quite powerful in the sense that we can see here lots of molecules inside a cavity. We can see some kind of complicated field distribution, and we can ask what's going on in our strongly coupled system. On the right-hand side here, I've got one of these dispersion plots. This one's in infrared. It's looking at vibrational modes, and it's a polymer between two metal mirrors again. And in this case, what's nice about this particular example, and why I've chosen it, is that we have one cavity mode coupled to three different vibrational resonances. And a question that's been in my mind for quite a long time anyway is, okay, really nice, but we've got 10 to the how many molecules in here, a large number. How do the individual molecules behave? What's going on? And if we're working in the optical regime, there's really no way we can actually ask that question experimentally. So we wanted to see if we could take advantage of other developments and make an analog system in metamaterials to study the same kind of thing. So that's what I'm really going to try and tell you about now in the next few slides. So here's our system. There's a photograph on the left here of this system, which is down to this PhD student who's been doing a wonderful job on this, Milo Baraklov. In the middle region here is our cavity. So there are three slabs of material here. Two of them make up the mirrors, front and back. The mirrors are just wire meshes, microwave frequencies, which is where we're working. We want to make a semi-transparent mirror, and a wire mesh is a good way to do that. And then for the molecules inside the cavity, we need some kind of resonators. And we're using a very simple system of split ring resonators. You design your ring. The ring produces both an inductance and a capacitance because of the split here, and that gives you a resonant frequency. So you can design your ring, design your resonance to match your cavity mode, or the other way around, or both. And to give you an idea, we're working roughly at 30 gigahertz. The wavelength's roughly 1 centimeter, and our cavity is 29 millimeters in size. Okay, let's look then at the response of a cavity with no molecules inside it. I've just got a transmission spectrum on the left-hand side here. So it's the transmission through the cavity as a function of frequency. And there are two nice clear cavity modes we can see, 4th order and 5th order. On the right-hand side, I've got the result of doing that same measurement, but now for a range of different angles. So we've got on a color scale the transmission as a function of incident angle and frequency. So we've got some kind of dispersion curve. And you can see the yellow regions are the high transmission regions, and we can see this nicely dispersing cavity mode. What happens now if we include all of these split ring resonators on a sheet inside our cavity? Well, what happens is what we'd hoped, that the split ring resonators with a frequency of just under 25 gigahertz have interacted with the cavity mode, and in the trace of blue trace on the left-hand plot here, you can see that the single cavity mode is now split into two very clean, separate features. And again, if we do the kind of thing where we measure the transmission as a function of incident angle, then top right over here, we can see that we've got a dispersion diagram. You can see that we've ended up with an upper polariton branch here and a lower polariton branch. The white dotted lines indicate the original split ring resonator resonance frequency and the dispersion of the blank cavity mode. We've used a coupled oscillator model just to kind of make a match with what's going on here, and the results from that are shown by the black dashed curve for the upper polariton branch and the red dotted curve for the lower polariton. And one of the nice things that you can get out of doing this coupled oscillator analysis is to look at the contribution that the resonators and the cavity mode make to these two polariton branches. And I've indicated that in the plot down below here. So for example, just take the upper polariton. In this region here, the upper polariton is just slightly more resonator-like than it is cavity-like. As we come out an angle, we reach a point where it's 50-50. And then as we go out at higher angle, this mode's moving away and following the dispersion of the cavity mode, so it's primarily cavity mode-like. And exactly the opposite is happening for the lower polariton. Now, what we wanted to do next was to see, okay, can we actually use the techniques of microwave experimentation to probe what's going on inside our cavity and see whether we can find out anything about this mixed character of our modes. And the answer, of course, is we can, because otherwise I probably wouldn't be talking about it today. But let me show you what happens. So here's the situation that we've been working with, and I've been showing you in the past few slides here. We've got our sample, two cavity mirrors, and then a sheet of resonators in between it. And we've been sending out microwaves from a source on this side, looking at the transmission that's picked up by a detector. And here, at some particular angle for this kind of system, we've got a transmission plot. So it's just the transmission as a function of frequency. There's the cavity mode that's the 4th order cavity mode that doesn't really do anything, but it's a nice clean mode. And then over here, we've got the two split modes. We've got the lower polariton here labeled B and the upper polariton labeled D, sorry. And then the original resonator frequency is this thing just down here. So to look at what's happening inside the cavity, we can switch detection scheme, and instead of looking what's transmitted, we can put a near-field antenna inside our cavity. Remember, the cavity is only 29 millimeters big, but that's big enough to get a small little probe in it. It's the kind of thing we can't do in the optical experiment. So we can get a little wire probe inside the cavity and look at what's happening. So what I want to show you now are data that correspond to sending in microwave radiation like this at some particular angle. basically the same thing as on the plot on the left-hand side. And then we're going to sweep the position of this antenna inside the cavity and map out what the field looks like across this sheet of resonators. So let's do that first of all for this feature here, mode A, the cavity mode that's not involved in anything. So here we are. This is a plot where yellow shows strong signal, blue is weak signal, and we're looking at the field strength inside the cavity as a function of position as we go across this sheet of resonators. So this is the sheet of resonators, and we're just mapping out what happens here. And two things to notice. The first is that it's primarily bright in the middle region here, and that's a result of our experimental technique. The illumination is simply stronger in this region than it is towards the edges. So that's just a limitation of our experiment. The other feature that I'd like you to spot here is that we've got these very clear dark bands that look a little bit like interference fringes. And these dark bands correspond to the period of the cavity mode because it's propagating in the plane of the cavity. We're coming in at an angle of 15.5 degrees here. So this corresponds to the propagation of our cavity mode. So these dark and light bands are the cavity mode. Okay, let's switch then to the frequency corresponding to this feature down here. We're going to switch to the frequency at which the resonators, if they're on their own, will resonate. And now the field map looks very different. It's very pixelated. And in fact, a close inspection of these data shows us that the pixelation that we see here, we're picking up field associated with the individual resonators. So it really does give us a sense of being able to map out the field inside the cavity, and it's really tied to the individual resonators. So in this case, this is molecule-like, and this one up here is cavity-like. So what we want to do now is to look at our two polariton branches. Let's look at the lower polariton first, feature B, and you can see somehow it's a kind of mixture of these two things. It looks pixelated, but there's perhaps a slight degree of banding, maybe, somewhere in between the two. Let's look at the upper polariton, feature D, and now, well, the banding looks much stronger. It actually has got quite a lot in common with this cavity mode over here, but the pixelation is still present to some degree. You'll recall that in a previous slide, we had the coupled oscillator model and the Hopfield coefficients to give us an idea of the contributions the resonators and the cavity mode make to the different polaritons. So we can make a direct comparison now between those things. So here we've got, again, just a repeat of the Hopfield coefficient plot. This is the angle here that we're looking at in these data. So let's just look at what happens. For the lower polariton over here, we've got a primarily pixelated looking plot. And you can see that our polariton here, it's down near the resonator end. So that's actually what we should expect. It doesn't look particularly cavity mode like.
Hi, Professor.
The upper polariton, yeah.
Yeah. We sorry to interrupt. We have another question.
Good.
Hi, Bill. This is Julian from UCSD again.
Yeah. Hello.
I have a question. So you are able to detect electric field intensity. Is this intensity or amplitude and also phase, or just intensity of the electric field?
So with the microwave technique, we are actually able to get access to the amplitude and phase information.
So what are we looking at here?
We're looking here at a snapshot of the electric field strength inside the system.
But you can equally image the phase of the electric field.
We could, I think, yeah. I mean, I haven't done it, but I think we could, produce an alternative set.
Do you have an estimate of how many resonators per cavity mode do you have?
Do you mean how many resonators are there in this entire field of view?
Or the ratio of the density of resonators per cavity mode, because that determines the number of dark states that you have, right? Like.
Yeah, absolutely right. Yeah. I couldn't give you a number off the top of my head. I don't think it'd be very hard to get it, but I don't have the number, so there's no point in me trying to guess.
But maybe across the longitudinal length, there is only one resonator per.
Correct. Yes.
Okay, which is very different.
Absolutely right. And unfortunately, this was one of the problems of lockdown. So the experiment to add more in was kind of about 2 days away, and we kind of left the lab, and so it's still sitting there waiting to go. There are quite a few experiments that, of course, we want to follow up with. But that's a very, very good point. Okay, I'll come
I
back
guess
to that.
One last very quick question. So,
yeah.
Wouldn't it be possible also to do like some sort of microscopy analog of this type of experiment, but with molecules, probing things in another frequency range?
It's worth thinking about, isn't it? I don't think it's easy. That doesn't mean to say that it shouldn't be tried or that it's impossible. I don't think it's easy for a whole host of reasons. One of them is that even if you can get down to the diffraction limit, that's still going to be a very large number of molecules, and the diffraction limit's going to produce something. Let's imagine that it's a spot that's, I don't know, 0.5 micron in diameter. The coherence dimension for one of the mode in a typical optical microcavity is probably only 10 microns. So you're already sampling a significant fraction of the cavity. So yeah, maybe, and maybe it would be a good thing to think about how far one could go.
No, but thank you. Yeah, this is very good.
Okay.
Thank you.
Well, it's a great question, because it helps me move to my summary slide for this section. So this metamaterial approach, what does it offer? Well, I think there are really two things. I've tried to emphasize here today that the near-field access is something that I think is really going to be a very powerful way of probing what happens inside these systems. But we should bear in mind that the metamaterial approach also allows us to really design systems at will. You produce a CAD file, somebody goes and knocks out a printed circuit board, and there's the sample, and you assemble it, and you've got pretty much a designer system. Joel, you mentioned whether we might be able to look at dark states, and I think that's a really important thing that one would love to be able to do, and perhaps there's potential here to do that. I'm not sure yet. There's certainly potential to look at the role of disorder, and that would be an interesting thing to look at. I think it's important to recognize that close to the parallels are between what we're looking at in this metamaterial approach and the molecular system. Our resonators are not molecules. They are very different. They're not molecules, they're not atoms, they're not even two-level systems. They don't store energy, for example. So although there's a good analogy, it's not going to be perfect, and there are some things that are going to be different about the way that they behave. But it's just a start. I think there are lots of interesting things that one should be able to do with this technique. So having got this far, I've covered what I wanted to say about the metamaterial stuff. So let me just summarize by way of conclusion for today's talk. Really what I've wanted to do is to convey some of the stuff we've been doing to use ellipsometry to probe strong coupling. And in particular, the little figure here is a reminder that the thing that we found most fascinating so far is this emergence of a second loop in this way of analyzing ellipsometry data when we look at strong coupling. And then the second is to really highlight the potential of using microwave metamaterials as a kind of artificial probe of molecular strong coupling systems, where perhaps there are ways of looking at questions that we've really struggled to look at in other regimes. So with that, thank you very much. And I'll hand back to Cheng.
In fact, Professor Barnes, so we still have several questions. So I will enable their audio, and then you can answer their questions.
Fine, good.
Hi, so I have a follow-up question to Joel's question about the coherence length. So you mentioned it was 10 microns, right? So does that mean the number of molecules that actually contribute to the peak splitting is, the number of resonators that fit within that 10 micron range, or am I wrong?
Matthew, that's just such a fantastic question that I can't possibly give you an answer to. I wish I could. I think part of the problem is that if we look at the standard kind of equation, and it was in the little bit in the middle of my talk that I kind of skipped over, the thing that matters is the number density of molecules in the cavity mode, not the total number of molecules. So providing we have a mode with some mode volume, and we fill up that mode volume with an appropriate density, we'll get the full splitting we expect. So it's not quite as simple as just saying, how many molecules have I got? How much splitting can I expect to see? It's really about fitting a given number of molecules into a particular mode volume.
Okay. Yeah.
I think there is to just add something briefly. I think there would be a lovely piece of work to be done in making. We typically work with a planar microcavity in the optical regime. You spin a polymer, you make metal films, blah blah blah, and we typically make something that's a centimeter in diameter or a centimeter square or something. It would be great to do that and actually shrink the lateral size of the cavity so that we go from being much bigger than the coherence length of the cavity mode down to comparable with or smaller, and see what happens to the splitting again in that case. And my suspicion will be that if we make the cavity smaller than the coherence length, then we will start to see the splitting fall. That would be my guess.
Okay, very interesting. Thank you.
Yeah.
And more questions. So yeah, I think Joanne, you can answer.
So hello, Professor Barnes. I have a question about the second part of your talk. First, could you please elaborate a little bit on the controllability of these systems that operate in a rather macroscopic scale compared to the actual experiments with molecules? And also, what kind of other features of molecular systems can be reproduced using these resonators? Like, for example, I imagine first, maybe vibration and nonlinearities or something like that. Could you elaborate a little bit, please?
Yeah, thank you for that. So let me just check the first part of your question. You were asking about, was it the controllability?
Yeah, I mean, in terms of how easy it is to like carry the experiments using these systems that operate at a different energy scale rather than.
So let's deal with the two parts of your question. They're really good ones. The controllability, it's superb. It's I won't say it's no effort at all, but it's relatively straightforward. If you're careful, you can really exercise exquisite control over the samples that you're looking at. We're making use of mirrors and resonators that are made by a computer-aided design process, so you can really very carefully specify what you want. We're piggybacking, if you like, on the kind of printed circuit board semiconductor technology to allow us to do that. When you've got those parts, then assembling them into the kind of cavity structure and putting stuff inside, with a bit of care, you can do a very good job. And certainly the student involved, Milo Barraclough's done a wonderful job at that. So there really is a very good degree of control. The area that's perhaps not as easy to control is the microwaves. So getting a collimated beam of microwaves and having a very clear, narrowly defined angle of incidence is not so easy. But there are challenges with any technique, and you can really do, I think, a remarkably good job. So good on controllability. You asked another question about whether one could mimic vibrational modes, nonlinearities, and so on. Vibrational modes, it's not clear to me how we would do that in this context. I haven't really tried to think about it before, but it's immediately kind of going to be tricky, I think, because we'd need to introduce resonances that are at a much longer wavelength, which in this regime, the microwave regime, means we're going to be looking at bigger structures, and they're very rapidly going to become bigger than the wavelength we're looking at. So that would be a problem. In terms of nonlinearity, that was something that we thought about trying to look at, and indeed we did quite a lot of experiments trying to introduce some nonlinearity. It's remarkably hard not to include nonlinearity, but to include it in a way that the components that go into the system are small enough that they don't perturb the system. And we didn't really get on top of that particular part of the problem, at least not yet. So some things are possible there, but not easy.
Okay, thank you very much.
Okay, well, thank you for the question.
Yeah, so we have several questions. So maybe Wei. Yeah, next one, Wei.
Yep.
Hey Bill, this is a very inspiring talk. I have a question about the antenna that you use. So would it also perturb your local field strength, and how would that change the strong coupling?
Yeah, absolutely. Yeah, really important question, of course. So yes, we've done, we've obviously done some background work to look at that. So the probe that goes inside the cavity is actually just an incredibly small piece of wire, and I'm not going to guarantee it produces no perturbation, but we're confident it produces very little perturbation. So it's a very good point, but I think we're pretty confident that what we're looking at is not a result of a finite-sized antenna.
Okay, got it. Thank you.
Yes, it's a good point, of course.
And maybe Luis, you can answer your question.
Oh, hi.
Hello, Luis.
Oh, hi. This is Luis Martinez from UCSD. So my question is, so this is a naive question. So what is the advantage or do you think that from this phase that you get from ellipsometry, from the reflection coefficients, can shed light on information regarding, I don't know, dynamical or static disorder of molecules inside the microcavity? I mean, you can get information regarding the molecular part of the polaritons. Do you use this phase?
I think so. The answer is kind of a twofold answer. Can we hope to acquire information relevant to that kind of thing? Maybe. But I think we should also be clear that there's no magic about ellipsometry. We're looking at reflected light from our range of strongly coupled samples and choosing what we do with that information and how we present it. And really using the ellipsometry approach allows us to do it in a particular way. And it provides a nice intuitive kind of picture of what's going on in terms of watching these loops evolve and what changes. Perhaps one of the advantages of doing this is that it's a commercial system. There are a large number of them available from different manufacturers. They're in general very well set up, but they're able to operate at really quite high speed. So if, for example, you wanted to look at what happens as some kind of chemical reaction proceeds, this might be a really good way to do it. We're just trying to take advantage of tools that people in chemistry and materials science might have used before and apply them to this problem. So I guess the one word answer to your question is maybe.
Oh, okay, thank you.
Thank you.
Yeah, several questions. So George. George, you can talk.
Looks like a microphone needs to go on somewhere.
Yeah, maybe we will. Yeah, I think we will ask the next representative.
Yeah, perhaps we can come back to George.
Yeah. So, yeah, Rodriguez. Yeah.
Hi, Bill. Hello, Bill. Can you hear me?
Said, yes, I can hear you.
Yes.
Hello.
Hi. Good to hear you. Yeah, thanks for the nice talk.
Yeah, likewise.
Bill.
Thank you.
So two quick questions. So it is known that the splitting that you measure in reflection is different from transmission and is different from absorption. So if I now you introduce the ellipsometry technique and you pinpoint that the creation of this loop as a new criterion for the onset of stroke coupling. So so if you were to compare that to the signatures in those other three observables, to which one can you place it? Where does it correspond? Because normally for a fixed coupling strength, I think you would see that the reflection should show a greater splitting than transmission, which then would show greater than absorption, right? So where in that ladder you would place your loop?
Yeah. Yes. Okay. So it's a good question. I'm not actually trying to place this kind of loop analysis in amongst those different criteria that you've talked about in terms of should we be looking at reflection or absorption or whatever. In particular, maybe worth just going back to the discussion at that point, and which what I wanted to try and convey was the point that the details of exactly when this extra loop emerges in this kind of analysis depends on the exact conditions that one uses for the experiment. So even something as simple as changing the angle of incidence by 5 degrees is going to change the exact point at which the second loop emerges. So I'm not trying to claim that the emergence of a second loop is going to be some magic bullet that gives you an exact analysis that your system is now guaranteeably in the strong coupling regime. But what we are saying is that if you look at the spectral signature of what's happening using ellipsometry, you can get a very nice, easy to see visualization of changes that are taking place. And you'll see in the archive paper that there's a comparison between the various different criteria one can find in the literature, not so much between do I look at reflection or transmission, but what do I classify as strong coupling? Do I have to look at the ratio, sorry, the mean of the two individual line widths that I started with, or some other criteria? There are a number of them around, and you can get a slightly different answer from one to the other. And we're just saying really here that, well, we've got another one. So if you like, actually what we're doing is just making things more confusing. But nonetheless, I think it helps us look at that whole business and see, okay, this choice of criteria for strong coupling, in a sense, it depends what it is that you want to really understand about your system, and which one of those you want to pick. And perhaps maybe the most valuable thing is to look at it from several different perspectives at once and then say, okay, well, here's the system. If we think about it in this way, we get one kind of indication about at what point do we reach strong coupling. If we look at it in a slightly different way, we get another one. So our system is one in which we go through these various different, not states, but kind of responses, if you like, for our cavity, and we can understand what's going on in different ways by looking at these different kind of signatures that we can see. So a bit of a woolly answer, I'm afraid, Side. I don't think there is a one answer and you can just say, bang, I've got that, so I'm in the strong coupling regime. I don't think it's quite that simple.
Mm-hmm. Can I for the clarification, so I would like to ask you something else very quickly. So in your measurement where of the, I guess it's reflection or transmission, I don't know, with the molecules in the optical cavity where you have the dispersion relation and the model next to it, I noticed that the line width of the lower polariton is significantly smaller in experiment than in the model. And so I'm a bit surprised by that. I guess if I would have guessed one will be broader, will be the experiment. But so I'm wondering if there is something deep in the physics there, or is just, you know, maybe the uncertainty in the permittivity that you put in the model. You know, there's been discussion about why the lower polariton.
So again, another good point. Short answer and a slightly not quite so short answer. Short answer is haven't analyzed it as fully as one would like to give you the answer that would be appropriate. Slightly longer answer is the model, we shouldn't expect a perfect match because the model is based on a Lorentz oscillator fit to the absorption spectrum for the merocyanine. And the match between the Lorentz oscillator model and the absorption spectrum that we have, it's not bad, but it's certainly far from perfect. So differences in width, I'm afraid, are something that are likely to emerge from the way that we've modeled that.
Okay, thank you very much.
No, thank you. Yeah, good.
Yeah, so we have Stefan, who also typed in the Q&A. So okay. Stefan, you can talk.
Yeah, hello.
Hello.
Thank you, Bill. My question is about your microprobe technique. Could you also use that to drive a single oscillator in the cavity and then see how the energy spreads out from this single oscillator to other ones?
I had not thought of that, Stefan. That's such a lovely idea. Thank you. When we can get back and try it, I'm sure we will want to do that. It's just such a lovely idea. My initial thought is I suspect the signal strength is going to be appallingly weak because, as I said, the probe that we're using, we've taken great care to use the smallest probe we can get away with so that we couple as little as possible to the system. So I suspect that we're going to be able to do very little, but it's such a nice idea. Yeah. Okay. I think it's a great idea. You know, take one molecule and actually supply it with energy at different frequencies and see what happens. Great. Yeah.
Yes. Yeah. So, Bin, you can ask your question.
Hi. Thank you for your talk. Can you hear me?
Thank you.
Yeah. So yeah, I have two
questions.
Yes. Yeah, I have two questions. So the first one is about. So as we know, for the collective electronic strong coupling, there are a lot of uncoupled molecules and also some external reservoir states, and it's also difficult to detect them using regular optical technique. I'm thinking if your ellipsometry method can provide some information or some insight on these kind of states. And my second question is about the metamaterial. In your last slide, you show some contour plot for a single one angle, which is off resonance. I'm wondering, if you go detect the resonant angle, I mean the 50-50 hybridization, if there is more like a significant feature due to polarizon states.
Yeah. Yeah. Okay. Great. I'm going to answer your questions backwards, if I may, Ben. So. As I mentioned when I was talking about the metamaterials stuff, we got some data, we got part through what we wanted to do, and then lockdown arrived and we had to leave the lab. So absolutely, we definitely want to go and look at some other points on that dispersion curve and check whether this contribution of the resonators versus contribution from the cavity mode tracks better. And certainly the 50-50 point would be a great one to look at. So that's nice. Thank you for that. Great point. Your question about the ellipsometry and whether we can use that to probe uncoupled molecules. I only wish I was confident that I could say, yes, this is going to be a great way to probe dark states and look at uncoupled molecules. But unfortunately, I don't think that's the case. And the reason is that it's a little bit like the question somebody else asked earlier, is that the reason is that the ellipsometric approach is really using the reflectivity information that we get, but in a slightly different way to the normal one. But we're still probing the system in basically the same way. We're sending in polarized light and we're looking at the amount of light that's reflected. And in the ellipsometric technique, we're also analyzing that polarization state. So I don't think, unfortunately, there's some extra probe in there that's going to get us into that happy situation that we'd all like to see, where we've found some way of probing what's happening within the reservoir, or looking at the dark states. So, no, sadly, my answer to that part of your question is I don't think so. Okay, I'm very happy if I'm wrong. I really would be very, very happy if I'm wrong. If somebody can figure out a way to do it, fantastic. Please go right ahead, and that would be lovely. But I haven't managed to think of a way of doing it.
I see. Thank you so much.
Yeah, so the next question from Connor.
Yeah.
I hear a voice.
Oh, sorry. I made a mistake. Sorry.
That's all right.
Yeah. Hello.
Hello.
Yeah. So I was trying to understand if that plot, the ellipsometry, the loops can be understood as a like suppose you have the transparent molecule, and as you increase the time, some molecules get converted to the opaque molecule, right? Like the myrocyanine.
Mm-hmm.
So can it be understood in a kind of a it's a statistical phenomenon? So can it be like the intermediate times you can see the superposition of the two extremes where you have full transparent molecule and full set of entirely filled with myrocyanine molecule, something like that.
I'm not sure I've really quite properly understood your question, but trying to see what I can, whether I've got this right. So what we can say is that if we look at this loop that we're seeing here, and we watch how the shape and the topology of the loop change with time as we expose this sample to ultraviolet light, we are watching the conversion of molecules from an inert state, the spiropyrin form, to this merocyanin form. So the number of merocyanin molecules in the cavity is going up, the number of spiropyrin ones is going down. So it's just a numbers game. There's no kind of interference going on here. It's just simply how much have we got of the absorbing molecule versus how much have we got of the inert one. And that's really the key thing that's driving this change in behavior that we see. Does that help at all?
No, actually, I was saying this because suppose you divide the cavity into two parts, and one of them you completely fill with merocyanin, and the other half you completely fill with spiropyrin, I think.
Yeah.
Then can you reproduce these loops?
So you're okay. So you're going to take a kind of sample, and in half of the sample,
exactly,
convert it from one form to another. And you're asking then if basically is this? Are you asking really? Is it reproducible? Can I cycle it round? Is that the?
Yes. Still, can you see the loops?
Yeah. So you know if you expose it to UV light and you get this change, if you then leave it for a long period of time, it will eventually relax back to the non-merocyanin form, and you'll get the original loop back.
Okay. Thank you.
I suspect that I've not fully understood your question, but this is one of those cases where it would be much easier if you and I could go and draw something on a piece of paper, maybe. But perhaps we can do something offline that might help you. I'm very happy to talk about it if you want to contact me, but I think we've probably got stuck at this point trying to do it online in this particular way, anyway. Anyway, thank you for the question.
Yeah, so we have two more questions. So David, yeah, I saw.
Hello, Bill, can you hear me?
David, I can hear you clearly.
Hello, greetings from Sheffield. I hope the weather in Exeter is rather better than here in Sheffield, and it's really grey and rainy. But anyway, I was really fascinated by your kind of analogy for strong coupling using the kind of metamaterials in the cavity. And I just really wondered, so first of all, how does the kind of wavelength of the radiation that you're putting into this cavity compare with the physical size of the resonators? Because of course, in a strong coupled cavity, we've got light of hundreds of nanometers, and the size of our atoms is like the size of a molecule is a few nanometers. And so, you know, how big is that analogy, and when does it break down? And then also, what's the kind of dephasing time, or can we think about a dephasing time for the excitation on the split ring resonators?
Yes. Okay. So we can think about both of those things. So first one, the size. So the split ring resonators in the data that I've shown you are 1.5 millimeters in diameter, give or take. Whereas the wavelength associated with the resonance is about 1 centimeter. So they're at kind of lambda by 6 or 7, that kind of thing. So very definitely well away from the equivalent molecular kind of comparison, but nonetheless, I think sufficiently sub-lambda that we can say they're well sub-lambda, by which I mean they're not close to a kind of lambda by 2 sort of size, which you could immediately start to worry about. So that's a good point. You know, where I was mentioning various things that you can expect a good analogy between the materials and molecular world in some regards and not in others. And size is clearly a very important one. We can't get down to the situation where we're very, very sub-lambda, but I think we're sufficiently sub-lambda that it's worth probing and looking at. In terms of the dephasing time, I haven't really thought about that very much. It's a really good point, of course, David, but I think all I could point you to at the moment is to look at the width of the resonance feature associated with the split ring resonators, and it's very comparable with the width of the cavity modes that we're looking at. So that's probably as close as we're going to get, I think, at the moment, in terms of answering the question of, well, you know, what's the kind of the resonator lifetime, if you like.
Okay. Thanks very much. I think, yeah, I think it's really.
And again, that's another good thing to think about, isn't it? So we spent a lot of time trying to work out what system we could put together where we get something reasonably comparable in terms of cavity line width and our split ring resonator line width. It's very easy to wind up with a situation where they're mismatched by a factor of 1,000, but clearly not of much value in trying to look at this kind of experiment.
I mean, presumably you can control the separation between the split ring resonators as well. And
absolutely.
Make
them absolutely. No, that's indeed, yeah. And what I could say here is that in this particular case, the way they're arranged is such that there's very, very little interaction between the split ring resonators when they're on their own without the cavity.
But is the separation between them smaller than the wavelength of the radiation?
Yes, it is. Yeah, the separation here is about 6 millimeters. So we're inside the light line, if you like, but not necessarily by a great deal.
Okay, thanks. Thank you very much.
Good. Really, really good things. Thank you, David.
Yeah, so one last question from Joel.
Okay.
Sorry, Bill, I don't want to prolong this much more. There are a lot of interesting questions here. So I want to follow up on the question of nonlinearities, because as you said, these are not two-level systems that can saturate, right? Like for me, these resonators are just harmonic oscillators. So
yes, indeed.
Can you elaborate again, what is the strategy to really introduce nonlinearities in this system? Is it by affecting the material making these resonators, or
yeah. So what we tried was to incorporate a little electric circuit with each resonator, which included a nonlinear element into it. So we essentially tried to build an electronic nonlinear component to add to our split ring resonator. And what we didn't manage to do was to do that in a way that provided us with a resonator that looked pretty much like the one we started with. The electronics that we needed to do that, and the components, literally the components that were required were simply too big and perturbed the system way too much. Now, somebody who's better at that kind of stuff than we are, maybe would have a good shot at being able to do that. And I don't see why. I'm not aware of an in-principle problem, so it would be a great thing. Maybe somebody listening at the moment might like to take that challenge on and try and figure out how to design a split ring resonator with some onboard circuitry of some kind that would provide that kind of interesting nonlinear response that would allow you to probe the kind of question you're asking.
So these are basically standard electronic nonlinear components, which I'm not familiar with, but maybe I can ask you later.
It turns out they're not that standard. They were quite hard to get hold of, and when we did, we discovered that actually incorporating them wasn't a trivial problem. And even when we did manage to incorporate them, the system that we ended up with was so severely perturbed that we didn't really have what we started out with. So
I see.
We kind of stopped at that point.
But otherwise, without those components, these things really behave just like harmonic oscillators.
Absolutely right. That's my view, same as yours. They're simply little harmonic oscillators. Yeah.
Thank you very much.
Okay.
Yeah, I think that's all the questions. So let's thank Professor Barnes again for this wonderful talk. And thanks everyone for the attendance and discussion. Yeah, I would say, yeah, we have too many questions.
Thank you for that, that's very kind of you.
Yeah, it's like, so I can share my screen probably. Yeah, so next week we are going to have the first postdoc spotlight with Dr. Christine Anadotia from University of St. Andrews and Dr. Bing Gu from UC Irvine. And also what I need to mention is that, in fact, the application for the postdoc spotlight is now open. So the application can be made here. And the second postdoc spotlight will be August 19th. So everyone, every postdoc is welcome to contribute. And that's for today. And hope to see you next week. And thanks, Professor Barnes, again. Thank you.
Thank you very much, Cheng Cheng. Thank you. Bye-bye.
Bye.